Here we are again, this time with section 2.3 of our textbook, which is about some graphics for, well, organization too, for quantitative data, such as the number of television sets in 50 randomly selected households. We have a lot of numerical observations, and we could take an average of these. So we could add them all together and find out how many televisions there were in all 50 homes. So that's how we know that this is a quantitative variable. And since these are counted items, that makes it a discrete variable. Okay, so our author has made a frequency table which shows both the actual frequency and the relative frequency for the number of televisions. This is fundamentally the same as the categorical frequency table that we had in the previous section. Here's another example of one of the things that's different about this is that it covers a wider range of values. We have many more different values than there were in the previous data set. In the first case, we had only 7 possible values here, but here we have a messier collection. So we're going to clean this up by grouping these observations in clusters, so to speak. So now we have categories 30 to 39, 40 to 49, etc. We'll talk about how we can get an average of these in time. Meanwhile, we have a tally for the number in each of the categories. Observe that the categories all have the same width and that they do not overlap each other. Something is either 89 or 90, but we don't have any way for any of the observations to fall into both of these categories. They have to be distinct, and they all have to have the same width, which in this case is 10 units. Each of these goes 10 units wide. Then the frequency and the relative frequency are done exactly the same way as they were before. So, there are some really inside terms about how these data are grouped with class limits, class width, and so on. Cut point versus limit. The book makes a big deal of these. I'm not going to make a big deal about them, but I will talk about them a little more when we're all together. And these terms, the limit and the cut point, are used in making a histogram. So here we have a histogram showing numbers of television sets and both their actual frequency and their relative frequency, and in this case the data are shown on scales of the same size, and the histograms look exactly alike as we would expect. But we can see in this case that, well, the scale isn't the same, but the shape is the same, isn't it? Here's a problem for us to do. We need to make frequency and relative frequency distributions, and we are going to make histograms for both. So in this case, the question, another convenience sample, the stat professor asked his students how many siblings they have. And we'll look at those data and work with them in just a sec. Okay, I picked up the data from the DVD, copied it onto the clipboard. Now I'm back in StatCrunch, and since I included the headline here in my text program, I'm going carefully to click and replace this column header with the one that's in the data. And here we have all the facts for number of siblings, and I'm looking at our table size. We have 40 observations. And what we want to do with this is build a frequency table and a relative frequency table. And we're also going to build a histogram. Okay, so stat tables, frequency tables. We have just one column of data here. We want both the frequency and the relative frequency in the same table. Why wouldn't we? And here we are. So, no one had more than 4 siblings in this group, and only one of those. 20% had none, etc. Histogram here. So, our information is siblings, and we're going to show the frequencies in this histogram. Okay, now you may say, what's the difference between this and a bar chart? In this case, there is no difference. The big difference in a histogram, and you will see this in Excel in particular, is that ordinarily in a histogram these are grouped. But if we don't have groupings of these, like 0 to 2 and 2 to 4, which would just evaporate all the meaning from this particular chart, then it does look just the same as a bar chart. Let's look at the next exercise. Number 58, on cheese. How much cheese people have consumed. I do find it interesting that once upon a time Americans were accustomed to eating 8.3 pounds of cheese per annum, and now look at us. Well, that's a lot of cheese, isn't it? Now I've pasted all of the cheese data into a new table in StatCrunch, and I'm going to make a histogram with this. My variable is cheese, and something we have here that we didn't see before was bins. My bins, according to the specs that I was given in the problem statement, start at 20 pounds of cheese per year, and we were asked there to make each bin 3 pounds wide. So now this histogram, this is one of the things that StatCrunch doesn't do so nicely. It should say 20, 23, 26, 29, etc. It doesn't. It leaves us to calculate those cut points for ourselves. And another thing I want to show you, which is interesting here, suppose that I had chosen a different bin size. I'm going to start at 20 again, but let's make the bins 5 units wide this time. Well, that gives us less information, doesn't it? We don't see that nice stair-step effect. We don't see that this category, there are actually 3 categories that have a good bit more than others. And of course we can make a third histogram with bins only 2 units wide. Now, this might be a bit too much information. It shows us gaps that are not really informing us of anything, because are we really interested in the difference between 32 and 34 as opposed to between 34 and 36? My thinking, looking at all 3 of these, is that this is informative. It says that the thing that we observe most often is close to 30 pounds. Of course, it's close to 30 pounds in each of these. Here we get a somewhat different reading because of the change in the cut limits. But we also get a nice smooth picture of the distribution. I'm not sure that this gives us information that we really want. What's the moral? Well, the moral is you need to look at various possibilities and make an informed decision. The one thing I can tell you about this is that ordinarily you do want to have an odd number of bins if you can contrive it that way. This is one of my favorite kinds of graphics because I like how it looks. It's very informative. It tells me both about the spread of the data, how wide that is, and it gives me some information about where the median might be or the mean. We can imagine a fulcrum down here. Where would we put a fulcrum to make this thing balance? Kind of a fun thing to think about. And it's also very easy to do one of these by hand. This is something that Excel will not do for you. In problem number 65, we are asked to take the ages of trucks on the road nowadays, or when they wrote this, and put them into a dot plot. Let's do that now. Okay, here in StatCrunch, I have 37 observations about trucks and how old they were in years. And behold, I have dot plot as one of the choices for my data. Now, if you think about it, this dot plot is definitely going to work best with discrete countable data. There we go. So we can change the size of this picture if we want to sort of spread these things out a little bit. I think that looks good, and of course we can copy it to the clipboard and so on as we did before. Next we have another winner, the stem and leaf plot. This, like the dot plot, gives you a lot of information about the distribution of the data, and it's very easy to make. I use these a lot when I am looking at test grades for students. Here we have a whole bucket full of numerical data, and we want to sort it out. So, since these are two-digit numbers, we're going to take the first digit, put that here, so 30-something, 40-something, 50-something, and so forth. And then we'll just walk through the data and write down the numbers that we get. If we want better information than that, which we may do when we want to make a box plot by hand out of this, I'll show that in class, then we write it again and we sort out the numbers on the leaves. Now if we imagine turning our heads on our sides, we can see, well, we don't even have to turn on the sides to see that definitely most of them were between 60 and 69. Here's another case, and this collection shows something interesting. We had a lot of observations in the 200s, in the 210s. So, what was done with these data was to instead put two lines for each stem, 190s, 200s, 210s, and so on. That spreads out the data, and you can see that here we have just 0 through 4, and then 5 through 9 for the leaves. And that gives us a very nice bell-shaped curve for this distribution. Unfortunately, making stems this way is something that StatCrunch cannot do. But let's look at what it can do with a stem and leaf plot. In this case, we have bottles that supposedly have 1 liter of soft drink in them. Well, they don't have exactly 1 liter. Someone came along and sampled the collection of soft drinks and measured exactly how much was in each one. Okay, now I have all of my soda contents in milliliters in a StatCrunch table, and I came here to make a stem and leaf plot. the stuff that I want is obviously the column labeled content. Let's just see what the program does left on its own. I don't want it to trim anything from my set, but the fact is I don't have any way out values in this case. Okay. I don't really like how these worked out. Notice that what the program took automatically was it did it in groups of 10. So this is 900 to 949. This is 900, well, 50s, 960s, 3 observations in the 960s, 4 in the 980s, and so on. Let's look back at the options that were here and observe that for leaf unit, I could have made it 10 or I could have made it 1. Let's see what happens when I make 1s. Okay, now it is making its leaf units just on the last digit, not on the last 2 digits of the data that we started with. And this spreads out the data quite a lot. And now if we turn our heads on our sides, we can see that it is high in the middle and low on both ends, as so many phenomena are. Okay, homework for this section. I want you to do every other odd problem, so 53, 57, 61, etc. Try to do it by StatCrunch, try to do it by hand. You may make different choices depending on which method that you use. That's the end for 2.3.